A row of plotting boards lies open under blackout lamps. Orders are read against a synchronized time signal. At 21:40, 882 British guns fire as one. In the first 15 minutes, over 125,000 shells land on pre-calculated coordinates along a 12-mile front. Corrections for wind, air density, and barrel wear were computed by slide rule days in advance. No ranging shots are taken. Signals later recorded by a German light division state that the barrage arrived complete, with communications cut in minutes and counter-battery locations smothered before reply. Pre-war doctrine had assumed observation was essential for accuracy beyond 8,000 yards in open desert. The data now shows otherwise. Predicted fire has replaced eyesight. If the calculations hold through the night, armored brigades will advance under a canopy of mathematics. The open question is simple and decisive. Can numbers, not armor, break the Axis front? The desert sun climbs over Cyrenaica in April 1941. Through heat-blurred binoculars, a battery commander of the Royal Artillery studies the horizon. The aiming post wavers as if afloat in the mirage. Phone lines crackle with bearing corrections that change with every gust of wind. Pre-war field training had assumed visible targets or short registration shoots to bracket the enemy. In the western desert, those assumptions collapse under the empty sky. Landmarks are absent. Mirage distorts sight beyond 3,000 yards. Enemy guns operate from reverse slopes, hidden from direct observation. At 10,000 yards, range errors frequently exceed 150 to 200 yards. Counter-battery fire arrives late and dispersed across the sand. British positions are bracketed by German 88mm batteries attached to Afrika Korps forward groups faster than the defenders can respond. The 13.4 thousand-yard maximum range of the QF 25-pounder means nothing if the gun cannot see what it strikes. The problem is stark. After-action notes from 13th Corps artillery staff in the spring of 1941 record the frustration in dry terms. No accurate datum points, calibration uncertain, dispersion unacceptable at 8 to 10,000 yards. The numbers tell the story. Internal tallies show over two-thirds of long-range rounds falling outside lethal brackets. The QF 25-pounder, the backbone of British field artillery, is accurate in theory. In practice, the desert strips away the tools gunners depend upon. Dial sights are set off improvised datums. Meteorological corrections are absent. Propellant lots vary in quality and power, especially in the early months of 1941. The German observation posts on high ground command the battlefield. British guns fire, adjust, fire again. By the time the correction lands, the enemy has moved or replied. The initiative belongs to whoever can see first and strike fastest. In the spring of 1941, that advantage lies with the Afrika Korps. The British artillery is outgunned not by superior tubes, but by superior geometry. A method is sought to remove eyesight from the equation entirely. Inside a training facility at Woolwich, London, in the autumn of 1941, a staff officer sits with a training pamphlet beside a slide rule. Firing tables are annotated with pencil corrections for temperature, barometric pressure, propellant age, drift, and barrel wear. The officer initials a revised page stamped, "Predicted fire." Traditional gunnery culture privileges the observer and the gun captain's intuition, his feel, for the weapon. The Directorate of Artillery now argues for a different path. Standardized computation. If every variable can be measured and corrected before a round is fired, accuracy becomes a product of mathematics, not luck. The Director No. 9, an optical instrument for indirect laying, allows guns to be aimed with fine resolution against grid coordinates. Survey regiments are formed to tie gun lines to geodetic grids using prisms and chains. Consolidated firing tables are printed and distributed under the heading Field Artillery Training, 1941. The innovation is conceptual as much as technical. Training circulars stipulate that visibility is subsidiary to computation when grid and survey are adequate. The implication is radical. If every gun is tied to a precise grid, and if meteorology is fed into standard corrections, first rounds can land within lethal brackets without a single ranging shot. Instructors at the Royal School of Artillery at LYDD run controlled trials. Officers practice quadrant elevation by mills, matching numbers on paper to trajectories in the air. The skepticism among veteran gunners is real. Can paper truly replace the human eye? A trial in Egypt offers the first answer. An unseen target at over 10,000 yards is struck by a first salvo concentration. No ranging, no registration. The guns fire on computed data alone, and the shells land as predicted. The result is noted, filed, and circulated. The method works. At Helwan, Egypt, between January and March 1942, the Middle East School of Artillery refines the method into doctrine. Inside a canvas classroom, chalk marks lay out wind vectors and quadrant elevations on a blackboard. Outside, a meteorological balloon rises into the hot sky to profile the upper air. Temperature, barometric pressure, and wind shear are recorded at intervals and transmitted as MET messages on fixed schedules. Battery officers practice time on target scheduling, coordinating salvos from multiple gun lines to strike simultaneously. Veterans remain doubtful. How can a sheet of paper account for the chaos of battle? The curriculum at Helwan answers with repetition and discipline. Barrel wear gauges are issued with replacement schedules. Charge temperature is managed to narrow muzzle velocity spread. Plotting boards enable simultaneous concentrations across multiple batteries. 6 consecutive rounds land within approximately 25 yards of an obscured target during a calibration exercise. The school report is filed with quiet satisfaction. Skepticism declines as groups tighten. 4th Survey Regiment Royal Artillery provides the geodetic backbone. Guns are tied to grids accurate to single-digit meters. Aiming points are established by theodolite. Orientation is no longer relative to a visible landmark but absolute to a mathematical datum. Once the grid is laid, any target with known coordinates can be engaged without observation. The desert, featureless and empty, becomes a coordinate plane. Every dune, every wadi, every enemy position is a number. The gunners no longer need to see. They only need to calculate. By March 1942, Corps Headquarters authorizes operational testing of predicted counter-battery fire in active sectors. The trials will happen under live conditions, with the enemy returning fire. If the method works in combat, it will reshape how artillery is employed across every theater. If it fails, British guns will remain at a disadvantage against German observation and mobility. The first tests are scheduled within weeks. The desert will judge the mathematics. Tobruk, Libya, lies under siege through the summer of 1941. A British officer spreads a captured sketch of his own gun pits across a table inside the fortress perimeter. High ground to the south dominates the map. A handwritten note in the corner tallies the cost. 10 guns lost this week. The besieged garrison expects steady losses to superior axis observation from elevated positions. 7th Medium Regiment Royal Artillery trials a different approach. Fixed bearing, map-only counter-battery missions are prepared using the new grid system. No registration, no ranging, just coordinates and computation. The results surprise both sides. Report times for hostile battery locations shrink from approximately 90 minutes to approximately 15. Ammunition expenditure per neutralized target decreases. An intercepted Axis note complains that British guns fire without registering. Accuracy alarming, the defenders notice the shift. Counter-battery effectiveness is rising even as direct observation declines. German and Italian batteries with elevated observation posts find themselves under fire before they can complete their own missions. The method reduces the window in which Axis guns can dominate. Counter-battery becomes proactive rather than reactive. The Fortress Artillery staff documents the change in weekly summaries. In May, counter-battery success rate stands at approximately 30%. By July, it exceeds 60%. The improvement correlates directly with adoption of predicted fire techniques. Survey teams work under fire to establish and maintain grid accuracy. Met sections provide updates despite sporadic Luftwaffe attacks. The entire garrison artillery operates as a coordinated system, sharing data and targets through a centralized fire direction network. A German battery commander captured in August provides testimony. He describes British fire as arriving from nowhere with no warning shots, striking positions we believed concealed. The psychological effect compounds the physical. Axis gunners become hesitant to fire, knowing each shot risks immediate retaliation. The initiative shifts. British guns fire when needed. German and Italian guns fire when they dare. Siege ledgers later reviewed show a pattern. Counter-battery lethality rises as observation falls. The reversal is driven entirely by geometry and discipline. The guns are the same. The ammunition is the same. What has changed is the process: survey, met, and math. In Cairo and Alexandria depots, through the first 9 months of 1942, crates marked Directors Number 9 and quadrants are tallied beside ammunition pallets. Inspectors weigh shell bodies on calibrated scales, checking tolerances to ensure consistency. Commanders have long prioritized tanks and aircraft in allocation debates. Artillery now demands specialized tools and standardized ammunition to make predicted fire credible at corps scale. The Ministry of Supply responds. Over 1,000 directors and thousands of quadrants are issued to theaters across the Middle East and Mediterranean. Shell weights are constrained to tight tolerances. A variance of more than 2 ounces per shell is rejected. Propellant lots are tested to hold muzzle velocity variation to the low 2-digit feet per second. Barrel wear gauges are issued with replacement schedules tied to round counts. Fuse lots are batch tested for timing consistency. Even seemingly minor details, paint weight on shells, storage temperature of charges, are standardized. The goal is to eliminate every source of unpredictable variance. Inspection certificates from mid-1942 record compliance. Tolerance bands are met across production. Standardized data entry becomes possible across batteries separated by hundreds of miles. A corps can now assume its guns behave alike, that corrections calculated for one battery apply to another. Industrial standardization turns field arithmetic into reliable battlefield output. This is not innovation in design. It is innovation in process. The 25-pounder itself is unchanged from 1940. What has changed is the ecosystem around it. Instruments, ammunition, training, and discipline. Artillery instrument repair sections are established at depot level. Damaged directors and quadrants are refurbished to original specification. Optical elements are cleaned and calibrated. Scales are verified against master standards. The repair network ensures instruments remain accurate under field conditions. A director damaged in transit or combat can be restored to tolerance within days rather than replaced after months. By late summer 1942, enough calibrated instruments exist to align every field gun from Cairo westward. The supply priority given to artillery instrument production rivals that of armored vehicles. Shells and charges are sorted by lot and stored under controlled conditions. Temperature logs are kept for ammunition storage. Met sections inflate balloons on fixed schedules. The entire system functions like a precision machine, coordinated across hundreds of miles. The investment in metrology and standardization will prove decisive. Accuracy is not luck. It is the result of industry, organization, and relentless attention to variables once dismissed as minor. First Battle of El Alamein, July 1942. A corps fire plan is pinned across trestles in a command tent. Colored tapes mark successive lifts and barrage lines. Survey notes are rubber-stamped no registration. Conventional wisdom expects heavy registration to precede any major barrage, revealing gun positions to enemy observation. General Claude Auchinleck's staff issues a predicted-only plan using a unified grid and centralized computation. The risk is substantial. If the plan fails, infantry and armor will advance into uncut wire and unsuppressed positions. If it succeeds, the Germans will face fire from unseen guns, arriving without warning. 4th Survey Regiment ties every battery to the corps grid with precision measured in single meters. Divisional commanders, Royal Artillery, coordinate lifts and neutralization tasks using pre-computed concentrations. The planning process takes days. Each target is assigned coordinates. Meteorological forecasts are integrated. Ammunition is allocated by priority. Communication networks are tested. The entire offensive is choreographed on paper before the first round is loaded. 0 hour arrives on the 1st of July. The barrage opens without preliminary. Within minutes, Axis communication lines are cut. Within an hour, forward observation posts report confusion in enemy positions. German counter-battery fire is slow, dispersed, and ineffective. British guns continue firing on schedule, shifting targets according to the timetable. Ammunition consumption falls markedly compared to prior registered barrages, yet effect equals or exceeds previous operations. Observer reports note enemy batteries neutralized before they opened fire. The timing advantage is decisive. Axis guns are engaged based on sound plots and aerial reconnaissance, struck by predicted concentrations before they can complete target acquisition of their own. The First Battle of El Alamein is not a breakthrough. The front stabilizes, but the artillery performance exceeds expectations at every level. Post-battle analysis quantifies the improvement. Counter-battery response time reduced by 70%. Ammunition expenditure per target neutralized reduced by 40%. First salvo effectiveness increased by over 100%. The data convinces doubters. Predicted fire is not experimental. It is operational. Orders are issued in August to prepare an even larger fire plan for the coming offensive. The staff begins work on Operation Lightfoot. The scale will be unprecedented. Over 800 guns, firing on computed data, synchronized to the minute. Lessons from July are incorporated. Met procedures are refined. Survey accuracy is increased. Communication protocols are standardized. If El Alamein in July proved the method viable, the October offensive will prove it decisive. The mathematics that worked for a corps will be scaled to an army. The desert will become a firing range, every position a coordinate, every target a calculation. Through August and September 1942, meteorological sections inflate balloons at dawn across the western desert. Coded tables of upper air density, wind, and temperature layers are radioed to artillery headquarters on fixed schedules. Previously, hot day, light wind served as shorthand for atmospheric conditions. Now, density and wind shear profiles are embedded in each gun's firing data. At 35 degrees Celsius, density drop pushes long shots high absent correction. At night, temperature inversion bends trajectories downward. Met messages provide layer-by-layer data to correct both effects. Royal Meteorological Service detachments work alongside artillery Met officers. Balloon launches occur every 6 hours, more frequently before major operations. Upper air data is transmitted in coded format. Temperature at 1,000 feet, 2,000 feet, 5,000 feet. Wind direction and speed at each layer. Barometric pressure at ground level. The data flows to Corps headquarters where staff officers compute firing corrections for each battery based on location and target range. Gun position officers integrate Met with charge temperature control. Propellant is stored in insulated containers to maintain consistent temperature. Charges exposed to desert sun can vary muzzle velocity by over 100 feet per second compared to charges stored in shade. A variation of 100 feet per second at 10,000 yards translates to over 50 yards of error. Temperature logs are maintained. Charges are issued from storage minutes before use. The cumulative effect of Met correction and charge control shrinks mean error to low single-digit percentages at maximum range. A preparation order for Operation Lightfoot mandates Met updates ahead of each phase and detailed charge handling instructions. Battery commanders are required to confirm Met data receipt before opening fire. Survey sections verify grid accuracy. Directors are checked against master standards. The system has matured from experimental to standardized. Every variable that can be measured is measured. Every correction that can be computed is computed. The goal is to make the first round as accurate as the 10th, the night shoot as precise as the day. Night operations are rewritten. Darkness no longer conceals hostile guns when sound plots feed directly into firing solutions. Acoustic baselines using 6 microphone arrays spaced thousands of yards apart detect muzzle blasts and calculate grid coordinates within seconds. Flash spotters observe muzzle flashes and triangulate positions. The data flows to counter-battery officers who task guns using predicted concentrations. The enemy fires once, revealing position. British guns reply within minutes, often before the hostile battery can fire a second salvo. The night becomes as dangerous for Axis artillery as the day. Met and sound ranging together create an all-weather, all-light counter-battery system. The desert offers no sanctuary. Fire reveals location. Location generates targeting data. Mathematics completes the cycle with lethal efficiency. Axis headquarters summaries in October 1942 reflect confusion and concern. Intercepts and captured reports repeat phrases: no registration, unseen fire. Impossible to predict. Italian RE division batteries and German corps artillery staffs rely on observation posts and visual cues for counter-battery work. Their doctrine assumes British guns will register, providing warning and location. British survey and map concealment deny those cues. Guns fire from masked positions tied to surveyed grids. Luftwaffe liaison flights search for muzzle flashes and fail to locate batteries before they displace. A captured German after-action report from September describes the problem in technical terms. British artillery operates with precision that suggests forward observation, yet no observers are detected. Concentrations arrive without ranging, striking positions with first salvos. Counter-battery response is ineffective due to inability to locate hostile batteries. Request air reconnaissance be intensified. The request goes unfulfilled. Luftwaffe resources are stretched across multiple theaters. The RAF maintains local air superiority over key sectors. German observation is degraded by both tactical and operational factors. Axis gunners lack equivalent meteorological data, standardized instruments, and sound-ranging networks of comparable density. German artillery remains effective when it can observe and maneuver, as demonstrated in earlier desert campaigns. The mobile warfare of 1941 favored German flexibility and superior observation from mechanized formations. Static warfare in 1942 favors British systemization and computational superiority. The nature of the conflict has changed. The Axis doctrine has not. Italian artillery units report similar frustrations. A report from an artillery regiment attached to the Littorio division notes, enemy fire arrives with regularity and accuracy from concealed positions. Our attempts at counter-battery fire reveal our locations without achieving suppression. Request allocation of additional ammunition and improved observation resources. Neither request can be met. Axis logistics are strained. Ammunition ships are sunk en route to North Africa. Supply convoys are interdicted by Allied aircraft and submarines. The artillery arm fights on reduced allocation while facing an opponent with abundant supply. A translated signal captured later notes British concentrations arriving without preliminary, with observation posts blinded by suppression fire before they can adjust. Axis counter-battery timing lags. Once communication nets are cut by the opening barrage, individual guns are isolated and suppressed sequentially. German attempts to adopt similar techniques are hindered by lack of survey capacity, insufficient meteorological resources, and doctrine that remains oriented toward mobile operations. The asymmetry is stark. British artillery operates as a unified, computed system. Axis artillery operates as dispersed batteries relying on direct observation and local initiative. Both sides have skilled gunners and effective equipment. The difference lies in method, supply, and systematic application of scientific principles to tactical problems. El Alamein, October 23, 1942, evening. Watches are synchronized across gun lines stretching 12 miles. Officers check chronometers against radio time signals. Tarpaulins are lifted from ammunition stacks. Firing data sheets are stacked by each layer, pre-computed for targets assigned days earlier. Gunners stand by breaches, waiting for the signal. At 0 hour, 21:40, the desert erupts. 882 guns fire as one. The sound is not sequential but instantaneous, a single continuous roar that carries for miles. Over 125,000 shells land in the first 15 minutes. The weight of metal is staggering, over 4,000 tons. Targets are struck within approximately 100-yard brackets without ranging or registration. Pre-selected Axis strongpoints, communication centers, and artillery positions receive concentrated fire. The barrage lifts and shifts according to timetable. Subsequent phases target defensive positions along the front line. No gun fires independently. Every round is part of a coordinated plan synchronized to the minute. Post-action records show Axis communications cut rapidly across the entire sector. Telephone lines are severed. Radio stations are destroyed or abandoned. Forward observation posts are suppressed or overrun. Gun positions are struck before coordinated reply is possible. A captured German report describes the experience. The barrage commenced without warning at 21:40 hours. All communications to forward units lost within 10 minutes. Counter-battery fire could not be coordinated. Individual batteries replied when possible but were rapidly suppressed by concentrated hostile fire. 8th Army Artillery operates under Corps Commanders, Royal Artillery, coordinating lifts and neutralization windows by timetable. Survey units have corrected zero lines by fine mills. Directors are aligned to grids verified within the previous 48 hours. Counter-battery groups task hostile batteries from sound and flash plots updated continuously throughout the night. Planned lifts execute on schedule with precision measured in seconds. Armor and infantry advance under mathematically timed protective fire. When German strongpoints resist, pre-registered concentrations are called down within minutes. Night summaries filed hours later record unusually high first-round effectiveness and rapid degradation of hostile communication net traffic. 8th Army Intelligence notes Axis message traffic declines by over 80% in the first hour of the barrage. German and Italian units report being struck, without warning, by accurate and sustained fire. The Axis front does not collapse immediately, but it bends under coordinated pressure. Counter-battery dominance is sustained into the second night and beyond. British guns fire, displace according to prepared plans, and fire again from new positions surveyed in advance. Survey parties work through the night maintaining grid accuracy as the front shifts. Met sections continue balloon launches on schedule. The entire artillery system advances with the infantry, maintaining computational precision under fluid conditions. The enemy cannot locate British batteries in time to engage them effectively. By the third day, Axis artillery losses exceed sustainable rates. Resupply lines are interdicted by Allied aircraft. Observation posts are suppressed by persistent counter-battery fire. The mathematics holds under the test of sustained combat. Numbers, not valor, dominate the battlefield. El Alamein, October 25 through 29, 1942. Night falls across the desert. A line of microphones sits half buried in the sand, spaced in a precise acoustic baseline extending thousands of yards. A plotting team sits in a sandbagged position, listening for the first report, pencils poised over triangulation charts. Acoustic detection has been part of artillery practice since the Great War. The difference now is speed and integration. Sound plots feed directly into the fire control system. Detection leads to computation leads to fire within minutes. Darkness traditionally reduces artillery accuracy by eliminating visual observation. British sound-ranging arrays and flash-spotting nets now deliver near-immediate coordinates for hostile guns firing under cover of night. The microphones detect muzzle blast. The analog calculator triangulates position based on arrival time differences across the baseline. Grid coordinates are produced within seconds. The data is transmitted to counter-battery headquarters by field telephone or radio. A counter-battery officer receives the coordinates, verifies they fall within assigned sectors, and tasks the nearest battery with a predicted fire mission. No registration. No visual confirmation. The guns fire based on computed data. Hostile guns are silenced in minutes, often before they can complete their original mission. Cumulative hostile guns destroyed over several nights reaches triple digits. Counter-battery logs show rapid suppressions attributed to sound plots, with precise timings noted against firing signatures. The method proves devastatingly effective. German batteries attempting to support counterattacks reveal their positions with the first salvo. British guns reply before the second salvo can be fired. Italian artillery units attempting night harassing fire find themselves under accurate counter-battery concentration within 5 minutes. The speed of response leaves no time for displacement. Gun crews are forced to choose: fire and risk immediate suppression, or remain silent and provide no support to their infantry. A German artillery commander captured on October 27 provides detailed testimony. Night firing became suicidal. Every time we engaged, British counter-battery fire arrived within minutes. Accuracy was extraordinary. We lost 4 guns in one night attempting to support an infantry attack. By the 5th night, batteries were ordered to fire only in extreme emergency. The British clearly possessed a method of locating guns in darkness we could not counter. The method proved scalable. What worked for a single battery at Tobruk now works for an entire corps at El Alamein. Sound-ranging sections operate across the front. Flash spotting posts observe from elevated positions. Counter-battery headquarters coordinates responses, allocating fire missions to batteries based on range, ammunition availability, and priority. The system functions with mechanical regularity. Detection, computation, and fire become a continuous cycle. Night ceases to protect Axis artillery. The advantage swings decisively. British guns operate continuously, day and night, under a unified fire control system that treats the battlefield as a coordinate grid extending through time as well as space. Axis guns operate in isolation, firing when opportunity permits, displacing when threatened, always reactive. The cumulative effect is attrition measured in destroyed guns, exhausted crews, and declining fire support for frontline units. By October 30, Axis artillery strength has degraded below effective levels. Ammunition stocks are depleted by defensive fire. Surviving guns are dispersed to avoid concentration of British counter-battery. Command and control is fragmented. Rommel's counterattacks lack the artillery support necessary to break through prepared positions. The arithmetic is unforgiving. British artillery fires over 1 million rounds during the battle. Axis artillery fires less than 1/4 that amount. The difference in volume is matched by a difference in efficiency. British predicted fire concentrates effect. Axis fire disperses across the desert, seeking targets it cannot locate with precision. The breakout follows as mathematics predicted. Once artillery dominance is established, armor and infantry exploit the advantage. The predicted fire system, tested in July and refined through September, achieves its designed purpose. It does not win the battle alone, but without it, the battle could not be won. Sicily, July 1943. A barge unloads plotting boards and survey equipment at a beachhead on the southern coast near Gela. Inland, a gun group of the Royal Artillery anchors its Director No. 9 on a newly established grid surveyed from coastal landmarks. Mountainous terrain was assumed to degrade predicted fire. Survey, MET, and centralized computation adapt the method to complex relief. The challenge is significant. Mountains create wind shear and temperature gradients more complex than the desert. Dead ground limits observation. Roads restrict displacement options. The artillery staff addresses each problem systematically. Survey parties work inland, extending the grid into the hills using theodolites and careful triangulation. MET sections establish observation posts at varying elevations to profile atmospheric layers accurately. Fire control centers coordinate across divisions, pooling data and allocating targets by priority. The desert system proves portable, but not without adaptation. Invasion artillery groupings coordinate concentrations under Corps Commander, Royal Artillery staffs. The first tests come during the advance on Catania in mid-July. German defensive positions on high ground overlook Allied approach routes. Direct assault is costly. Artillery is tasked with suppression and neutralization. Concentrations are planned using predicted fire despite limited observation. The results match desert performance. German positions are struck accurately. Counter-battery fire is sporadic and ineffective. Infantry advance under protective fires that shift ahead of them according to timetable. Concentrations in Italy eventually reach several hundred guns per mile of front. The density exceeds anything achieved in North Africa. First salvo predicted concentrations support assaults amid terrain masking and limited observation. Centralized fire direction center schedule, time-on-target missions to minute-level precision. Multiple batteries fire from dispersed positions. Rounds time to land simultaneously on a single target. The effect is devastating. German observers report simultaneous impacts across the entire target area, providing no opportunity for personnel to take cover during preliminary rounds. An Italian post-war assessment characterizes British artillery as acting with mechanical regularity, noting the near impossibility of timely counterfire. The regularity is not mechanical. It is mathematical. Survey ties guns to grids even in broken terrain. Met corrects for complex atmospheric conditions. Standardized instruments and ammunition eliminate variance despite difficult logistics. Centralized control coordinates fires across divisions operating in parallel sectors. The result appears mechanical because it is systematic. The advance through Sicily demonstrates that the system developed in the desert proves adaptable to forests, mountains, and river valleys. Salerno in September 1943 tests the system under the most challenging conditions. Amphibious assault against prepared defenses with limited maneuver space. Artillery must operate from beachheads with restricted deployment areas. Survey must be established rapidly under fire. Met data must be gathered in unfamiliar terrain. The system performs. Concentrations support the lodgment. Counter-battery suppresses German artillery attempting to interdict the beaches. By the time the front stabilizes inland, British artillery is functioning with full computational capability. Cassino in early 1944 presents a different challenge. Static warfare against fortified positions in mountainous terrain. Artillery is required to deliver precise fire against bunkers, observation posts, and supply routes in a compact area where friendly and enemy positions are separated by hundreds of yards. Survey reaches extreme precision. Met updates are provided hourly. Fire missions are planned with care to avoid short rounds. The monastery atop Monte Cassino is engaged by predicted fire in February. The structure is destroyed with minimal expenditure of ammunition. Controversy surrounds the decision to fire. The execution is flawless. Prediction, not visibility, governs artillery employment across differing geographies. The revolution begun in the desert spreads to every theater where British and Commonwealth forces operate. By 1944, the method will be the Allied default from Italy to Normandy. Other armies study and adopt elements of the British system. American artillery incorporates similar techniques, adapting them to different organizational structures. Soviet artillery develops parallel doctrines, driven by different constraints but arriving at similar conclusions. The weapon is not the gun. The weapon is the method. Mathematics has replaced eyesight as the foundation of modern artillery employment. Italy and Northwest Europe, 1944. A core operations room displays acetate overlays for simultaneous concentrations across dozens of batteries. A staff officer writes "no registration" across the day's main fire plan. The notation is routine now, no longer experimental. Pre-invasion fears for Operation Overlord predicted confusion across vast gun parks numbering in the thousands. In practice, standardized MET, calibration, and survey allow synchronized barrages on an industrial scale. 21st Army Group Artillery and 2nd Army coordinate corps-wide, time-on-target packages and counter-battery missions with precision unimaginable 3 years earlier. Range error averages fall below 24 yards at long ranges under favorable conditions. Synchronized fires involve thousands of guns dispersed across hundreds of square miles. Predicted concentrations become routine for targets from enemy artillery positions to road junctions to assembly areas. Ammunition economies are recorded alongside increased suppression effects. Less ammunition achieves greater effect. A post-action note from a field army states, "The first round is now the last warning," summarizing the doctrine's maturity. Enemy units under fire have no opportunity to disperse or take cover after ranging shots. The first salvo is lethal. What began as desert adaptation has matured into a standardized Allied artillery system shaping every offensive from Normandy to the Rhine. The transformation is doctrinal, not technological. The QF 25-pounder remains the backbone of British field artillery throughout the war, largely unchanged from 1940. Medium guns and heavy artillery use the same principles. American 105mm and 155mm howitzers operate under parallel doctrine. The equipment is different. The method is universal. What changes is everything around the guns: training, instruments, ammunition standards, meteorology, survey, and command structure. Gunners are trained to trust the data over their instincts. Survey parties establish grids before the guns arrive. Met sections provide atmospheric data on fixed schedules regardless of tactical situation. Fire control centers coordinate missions across boundaries that once separated units into isolated fiefdoms. The artillery becomes a single instrument played by a central conductor. The symphony is mathematical. The result is overwhelming. By 1945, Allied artillery operates with a confidence and lethality unmatched by any opponent. German artillery, technically proficient and equipped with excellent weapons, cannot match the systematic application of computational method. Soviet artillery achieves similar density but with different techniques, favoring mass over precision. Japanese artillery in the Pacific faces American forces employing predicted fire adapted to jungle and island terrain. The British method spreads wherever Allied forces operate. Post-war assessments will attribute decisive weight to this transformation. The gun is important. The method is decisive. London, 1945. War's End. A bound report lies on a Directorate of Artillery desk. Graphs plot error reduction over time, a downward curve from 1941 to 1945. Ammunition curves bend downward, showing efficiency gains year over year. Suppression rates trend upward, reflecting increased first-round effectiveness. Public memory often credits armor and air power alone for Allied victory. Cinema and popular history emphasize tanks and aircraft. Directorate summaries emphasize computation, survey, and MET as decisive enablers of operational success. Royal Artillery Directorate compilers correlate instrument supply with accuracy gains. The data shows clear relationships. As directors and quadrants are issued, accuracy improves. As survey capacity expands, first-round effectiveness rises. As MET services mature, ammunition expenditure per target declines. Training staffs document curriculum changes from 1941 through 1945. The evolution from traditional gunnery to computational method is recorded in syllabi, training schedules, and examination results. Predicted fire efficiency multiplied several-fold since the dark days of Cyrenaica. A gun that required 20 rounds to neutralize a target in 1941 requires 5 rounds in 1945. The improvement is not in the gun. It is in the system around the gun. Ammunition waste reduced significantly, freeing logistics for other purposes. Time on target accuracy reported in the mid-90% range by 1944 and 1945. A concentration planned for 0-hour strikes within 30 seconds of schedule under normal conditions. The precision enables infantry commanders to plan advances with confidence in artillery support. A concluding line in the Directorate report reads, "The mathematical method of concentration proved decisive in enabling operational maneuver against prepared defenses." The sentence is understated. The revolution it describes reshaped warfare. Numbers replaced guesswork. Survey replaced landmarks. Meteorology replaced intuition. Centralized computation replaced individual judgment. The artillery arm became a scientific instrument underwriting operational success from North Africa through Italy and into Northwest Europe. The transformation did not depend on a wonder weapon or radical technological breakthrough. The guns of 1945 are not fundamentally different from the guns of 1940. Some are newer, some are larger, but the 25-pounder that opened fire at El Alamein fires the same ammunition to the same range as the 25-pounder that fires in Germany. What changed is method. Discipline replaces improvisation. Standardization replaces variation. Computation replaces estimation. The result is a multiplication of effectiveness without a change in equipment. The lesson is simple and profound. In war, As in mathematics, precision matters. The side that measures best, calculates fastest, and applies method over instinct holds an advantage that courage and tradition cannot overcome. At El Alamein, that advantage decided the battle. In Italy, it enabled the advance. In Northwest Europe, it supported the final offensives. The artillery revolution was quiet, technical, and decisive. It is written in firing tables, met logs, and survey records. It is measured in reduced error and increased effect. It is remembered by those who served the guns and those who advanced under their protection. The mathematics of 1942 remain relevant in the 21st century. Modern artillery still relies on survey, met, and centralized fire control. The tools have evolved. GPS replaces theodolites, computers replace slide rules, digital communications replace field telephones. But the principles endure. Predicted fire, born in the Western Desert under blackout lamps and plotting boards, proved that numbers could replace eyesight. The lesson transformed not only British artillery, but the doctrine of every major military force. The soldiers, surveyors, and Met officers who built the system in Egypt and Libya left a legacy measured not in monuments, but in method. Their work proved that war, at its foundation, is a problem of applied mathematics. The side that solves the problem fastest and most accurately gains an advantage no amount of courage or tradition can overcome. El Alamein demonstrated that truth with finality. 882 guns firing as one, synchronized by clocks and calculations, delivered a verdict written in numbers. The archive preserves their work. Firing tables, met messages, survey logs, and after-action reports document the transformation. The data does not lie. Accuracy improved. Ammunition waste declined. Lethality increased. The enemy could not adapt fast enough. By the time the Axis recognized the nature of the British advantage, the mathematics had already decided the outcome. The guns spoke in a language older than warfare itself, the language of geometry, trigonometry, and physics. The British learned to speak it fluently. Their opponents did not. The story of predicted fire is not a story of heroism alone, though courage was present in every battery under fire. It is not a story of innovation alone, though intelligence was applied at every level. It is a story of discipline, standardization, and the patient application of known principles to chaotic conditions. The desert offered no mercy. The British artillery offered no registration. The result was inevitable. Mathematics, in the end, prevailed. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.